Hey everyone, this is Dan at SPE Motorsport. This week, it's Turbo Tech. There's a lot we can get into with this. We're gonna kind of keep it short and sweet and talk about some of the differences between journal bearing, ball bearing, different options, and how to make your turbochargers live longer, talk about reliability, things of that nature. So up here, what we have right now is our Strike VGT to my left, and on my right, we have our Emperor turbocharger. These are more factory-based turbochargers. They're replacement type stuff for a specific model, but this kind of applies to like universal turbos of this nature, whether it be journal or ball. Just turbochargers in general as well, but that's what we have up here. So first things first, let's talk real quickly so that everybody knows how turbos function. All right, so the basics of how a turbocharger operates. I know everybody's gonna be like, oh, I already know that, but we need to at least talk about it real quick. Exhaust side, so this side is the turbine side, and then your compressor side, this is exhaust. Most of these are like an Inconel based steel, and then you have your aluminum compressor side. So hot side, cold side. You're gonna drive this side with exhaust from the engine, and that's gonna spin, and therefore on the compressor side, suck clean air in, compress it into the intake manifold. They're a very simple part that is also super complex all at the same time. So that's the basics. They're not, honestly, they're not super difficult to understand. They're pretty simple. One of the main things that we want to talk about in this video are the different bearing types. So you have two different bearing types pretty much in every turbocharger that exists in the industry, whether it's factory or aftermarket, doesn't much matter. You have journal bearing and you have ball bearing. On a journal bearing turbo, you have a bearing assembly. Keep this kind of split up so we can see it here. You have a bearing assembly that relies on an oil film. So the shaft, as this spins, the shaft is actually relying on an oil film to float the shaft. So you have to push pressurized oil into the turbocharger to create a film so that the shaft isn't riding on metal. Oil pressure is a big deal. The tolerances, obviously, when engineering a turbo like this, your tolerances are a big deal. There's a lot of stuff that goes into it, but it's a very simple principle. It's very similar to, say, a normal bearing in an engine. You're relying on an oil film to create essentially suspension for that part. What you have here is your thrust bearing. This bearing, when installed in the center section, obviously, this bearing controls what it is and what it's called, thrust, which is axial in and out. So that is controlling all your back pressure from the exhaust is always constantly pushing on the main turbine shaft. Your thrust bearing's isolating it axially in and out, so going this direction. And then your up and down, I guess your radial, so to speak, would be shaft to journal bearing. Well, the journal bearing itself is, as I just explained, just that round piece that's going to create your film. That's going to deal with it kind of going up and down. So that's why, and I know everybody's done this, if you've ever touched a turbo sitting on a shelf, the first thing that you're going to want to do to it, I'll show you, and you're all going to know exactly what I'm talking about. You want to grab it and you want to go like this. And you're like, oh, this thing's junk. Listen to all that play. Okay? Here's the thing. When you fire that vehicle up and you create oil pressure, all of that goes away. So what you're feeling inside that turbo when you're doing that is your tolerance in this bearing. All you're feeling is that play. When that oil film is in there, that play goes away. Biggest thing with turbochargers in the journal bearing form is don't use that to judge them. The main thing that you're going to want to use to judge that is your in and out. So the biggest thing, and this is just general turbo knowledge, on a journal bearing turbo, you're going to want to push it in and out like this. you're gonna have a tiny bit of play, but if it's going clunk, 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 you know, huge amounts of movement, that's an issue. That means the thrust bearing's wiped out. You got a lot of problems. So that being said, on journal bearing turbochargers, one of the main things that takes the brunt of all the forces is from the back pressure, is that thrust bearing. You know, there's different types. So on a thrust bearing, you have 270 degree, and then normally the upgrade from a 270 is a 360 like this, where it's the full circumference that it's actually riding on. This is a 360. That's every turbocharger that we engineer, design, sell, whatever. If it's journal bearing, it's going to come with a 360 degree thrust. So that's kind of like a standard thing in the performance industry nowadays. It used to not be, but it is now. So that is your basic functionality of the journal. Ball bearing is exactly what it sounds like. It's not overly complicated. They are ball bearings. Now, if you look at, this is one of the pieces out of what we call a center cartridge. Here's your actual center cartridge here. We have one that goes in each end in this particular turbo, so it's a dual ball bearing setup. Actually, there you go. There's a used one with a ball bearing in it. You can kind of see it. You're going to look at this real quick and you're going to be like, oh, it looks like a skateboard bearing. It kind of does. It's very similar. Obviously, though, they're very different. So on the ball bearing stuff, you're going to have any of the good turbos. Not saying you can't get turbos with this, but most of them are ceramic ball bearing. So when you're talking in a performance line of turbochargers in the performance world, most of them have ceramic balls in them. And the balls are very hard. They're just like steel, but they're way lighter, way less rolling resistance, et cetera, et cetera. So one of the major differences, though, that we'll get to first is a ball bearing turbocharger does not require large amounts of oil volume and or pressure to function right, because the balls, the way that they're designed and work inside this casing, it's just not required to make them function. So it needs it to take out the heat, but as far as keeping it from, say, the shaft moving too much or touching stuff, it's just not required. So your oil volume, your oil consumption in a ball bearing turbo goes way down. And those are like your major differences in that. On a ball bearing turbocharger as well, you're dealing with your axial loads like we were talking about with the journal bearing. You have your thrust bearing and a journal bearing. Well, the cool thing with ball is if you have two of these ball bearing setups in the center cartridge, you're dealing with axial, radial, everything out of just one bearing. So when you start eliminating, say, pinch points in the bearing setup or drag, so to speak, you're allowing it to spin more freely. And it's the same thing with just the general functionality of a ball bearing. Like they clearly spin easy. That's the whole point of it. So the point and the differences of, journal to ball, usually they spool quicker. So it takes less energy to spin up a ball bearing turbocharger, and obviously a journal bearing is going to have a little bit more drag because of the way the bearing cartridge functions. So, all right, guys, let's talk about the elephant in the room. This is the common question that we get. I feel like it's a day-to-day kind of thing. Do I go with ball bearing or do I go with journal bearing? It really comes down to the use and what the consumer wants. There really isn't a right or wrong answer. So like if you're doing a bigger turbocharger that has a lot heavier turbine and compressor wheel setup in it, just a bigger turbo in general, and you want something that's quick spooling, ball bearing's the way to go. It's a no-brainer. If you're more worried about just the robustness, reliability, and you're more or less using it in more of a stock form, journal bearing's great. It comes down to what the customer's using it for and not so much a right or wrong answer. Let's go into some reliability stuff. This whole bearing pack is designed to work in a certain way with a certain set of forces. So if you're overspeeding this, and when I say that, I mean, let's say this turbo and its combination you're using it was, fine at 30 pounds of boost with an even back pressure to boost ratio, meaning say 30 pounds of exhaust pressure, 30 pounds of boost pressure, 1-to-1, which is ideal. Say you're running that, turbo lives all day. It's perfectly fine. It loves it. Let's say you want to make 50 pounds of boost and your back pressure starts getting out of whack. You could have all the oil pressure in the world going to this shaft, but now you're overspeeding it to make more boost pressure, and your load against the thrust bearing and your shafts radially against the journal bearing now is at a point where you can't control it. So you take two dissimilar metals and basically fuse them together because you push out that oil film, and then you start touching brass to Inconel and you're just jamming that together. And what happens is it gets hot and it fuses, and then everything kind of becomes one. So once again, journal bearing's great if you're using it within its means and using it in the proper manner. And it's not much different with ball bearing, but we're going to get into that now and kind of explain why the ball bearing may be a little bit better in a scenario like that. So the nice thing with ball bearings is you're utilizing the ball bearing, say in this situation where we have a ball bearing on each side of this cartridge, you're utilizing the ball bearing for axial and radial type play. So now you have it dealing with the force of the thrust and the radial rotation of the turbine shaft. So that being said, if you overspeed it slightly or go a little bit out of its range, these will deal with a little bit of overspeeding better than the journals, in my opinion. So you get a little bit more forgiveness, I guess would be the way, but at the same time, they're more susceptible to neglect. So the big thing with the ball bearings, and really it kind of ties into the journal stuff as well, but being the way the bearing is kind of just bathed and it's not really a film, you can't get contaminants in these. So if you get oil contaminants, you're not changing the oil enough, your motor's sludgy, whatever it may be, and you start jamming that through there, you have to think about this. As this bearing is spinning, this thing's sitting in there spinning at 50 to 80,000 RPMs. So your shaft speed could be upwards, hell, there's some turbos that are upwards of 100,000. So you have to think about that. That thing is sitting in there spinning that fast. And ceramic ball bearings are really, really hard. So they're very brittle, So obviously if you ingest, say another little piece of metal or anything like that, that's a huge issue. That's basically you're killing it. What we're going to touch on now is basically allowing your turbocharger to cool off. So if there's anybody watching that, came through the automotive world in the early days of like turbo timers, ball bearing turbos, as I said, can't take any contamination well at all. So what happens is let's say you're driving your truck. You got high EGTs, you're towing a trailer up a hill, and you're really working it hard. You have the turbine housing really hot because you're pushing exhaust through it. If you have an EGT gauge on it and it's 1200 degrees, more than likely the physical turbine itself is probably that temperature, if not higher. And let's say you're the guy running the truck, beating on it really hard because you have to, because you're towing a trailer. Let's say you pull into the gas station and you're rolling up and you get to the diesel pump and you just shut the truck off. So I want you to think about what's happening in that situation. So clearly everything's super hot. You had oil pumping through the center section of the turbo, pressurized, it's bathing these ball bearings and coming out the bottom, obviously going back to the pan. Well, at the rear side of this center section, this is where the turbine slips in. So what happens is you now have heat, oil, and a lot of RPM that turbo is still seeing when you shut it off. So the oil, as I was saying earlier, is cooling the bearings as it kind of bathes over and flows over it. Well, when you quit pumping the oil, when the engine shuts off, that oil stays there. So what happens is you have a seal at the back side of the turbine where it is actually going in here. What I'll do is I'll put this through so you can kind of see what's going on here. So I'm going to slide this in. There's actually bearings in this already. We'll go ahead and slide this together. So you're going to see on here, there is a ring seal similar to a piston ring, and it's a pinch seal. So actually here, I'll show you that first. So if you look at that, it basically looks like a piston ring. Very similar. It is a compression style piston ring, and it's square edge. It's a little bit different, but you get the idea. And that is using tension. It's a spring tension to create a seal at the backside, the turbine side of the turbo in the center section. So what I'm going to do is I'll slide this in here and you'll actually see how that works. So we'll get that in there and then kind of set it in the chamfer there, and then it pops in. So you can hear that tension, and you can actually see how that sits in there now, and the gap and how close everything is. You know, that's probably a lot of what I'm going to explain here in a second, is showing you this distance and how tight everything is together. So what happens is you now have oil that is building up and just now laying on the back side of this. So what I'm going to show you now is a used turbine on one that failed. I'm going to kind of show you what's going on here. So this is no longer stuck, but what happens is you get oil soaked around this piston ring seal, and what happens is when that's compressed and inside that housing, it coats it up and it basically cooks it down. So that spring tension and everything that you've had on that seal is now basically gone, because the housing's pushing it together. You get the oil in there, it cooks because you're not now cooling anymore. You're no longer cooling because you're not flowing the oil through the turbo. So it cooks and then holds that seal tight. Now that the seal's held tight, you're going to fire this truck up after you put fuel in it, right? Take it back down the road. So you fire the truck back up, get out on the highway, you're hammering it again. You got 1200 degree EGTs, 1100 degree EGTs, say when you're going up a hill. And now that you've lost the tension on the seal and this is all coked up, what do you think happens? So what happens is you get this cup. Let me actually grab one here real quick. Keep rolling. This cup, this is a clean one, sits right here, and then the turbine goes in. So this cup's sitting like this. And I'm going to show you the cup from this turbine. And what it is basically, it's essentially a heat shield to help deal with some of the exhaust. That's what happens. So all that oil and coke and everything that kind of built up the exhaust fume, or everything that's coming out of the engine, all your soot and whatnot, is going to build up into that. So that builds up behind there, but now it's also kind of sticking to that seal and getting in there. And then what happens is, what I just showed you ends up pushing past that piston ring, or that ring seal is what it is. It pushes past, and then look what's right on the other side of that seal. This is where the ring seal is riding, right in here. And then as soon as it seeps past that, guess what's right behind it? A bearing. So essentially what's going to happen is you're going to get all these hard deposits. So you're going to take one of these little granules, it might be a huge piece, who knows at this point. You're going to take one of these hard pieces, you can hear how hard that is. That is going to make it past that seal, and it's going to get into that bearing. As we discussed earlier, you have an object that's spinning extremely fast, and then we're going to induce something that's extremely hard into that. So yeah, it's not a piece of metal like this, but you can see how hard that material becomes. So what happens is you put that in between these balls and then they try riding over it. And when it tries to ride over that substance that's extremely hard and sticky because it's in oil, it sticks to the cage, and then that bearing tries to ride it, the ball bearing then tries to ride over top of that other hard substance. And what happens is exactly what I'm going to show you right here. This is, which we may not be able to see, but we'll try our best here, this is a ball bearing that blew apart. So it's literally in half. So what happened, here's a good one. That's a full size one. And then this one actually had a piece go through it and it blew the bearing apart. So the problem, now this is, taking a step back with this reliability thing. The problem with this versus journal is obviously journals deal with those issues completely different because they're riding on an oil film. So they're not as susceptible to that as a ball bearing is. Now, what happens whenever you do this with a ball bearing is you create gap. So I'm going to show you on this one. This is actually the center section that this came out of. Look at this huge gap that we have now. So when you knock one of these balls out of here, yeah, the other ones may be perfectly fine, but now you're not dividing the load evenly across that whole range. So now you induce a bunch of other things. And when I say other things, I mean oscillations, which change with RPM. There's a bunch of things that it causes. So eventually the demise of that turbo doesn't take long. Being that you have a 5 millimeter in our turbo, in this particular one, you have a 5 millimeter ceramic ball. Once that thing jumps out of there and you start knocking a couple out, now you just have a space of 5 millimeters. So that's definitely a negative for the ball bearing. Now, you have positive and negatives for both. I don't want to try to sway you away from ball bearing, but this is a scenario that if you're abusing the truck or car or whatever it may be, if you're abusing it and you're not taking care of it in the essence of letting it cool down, this can happen. It's not uncommon. So just because they're stronger doesn't necessarily mean that they're more reliable if they're not taken care of, if that makes any kind of sense. So once again, your choice is going to come down to what the customer needs and wants. And I personally, I like the fact that ball bearing turbos spool quicker. I really do think they perform way better, but you just have to use your head with them. It's like anything else. If you have a bunch of really good positives, obviously there's give and take. So, if it's kind of like a big camshaft in a small block, if you have a bunch of extra lift, yeah, you're going to make way more power and move way more air through the motor, but down low, you're going to lose some torque. So same thing here, there's give and take from both ends, but that's something that can be a huge problem with the ball bearing stuff. So like I said, more susceptible, easy way to take care of it is let it cool down. Act as if though you have a turbo timer, pull in, let it rest for a little bit, let it cool off, then shut it off. You know what I mean? So yeah, so that covers the reliability stuff. And I want to touch on some of the things that our customers may call in and say like, hey, good for instances on the ball bearing stuff. We'll go over this real quick since we're already on it. Noise. So clearly a ball bearing is going to be noisier than a journal because journals are riding on a film of oil. There's nothing really extra moving in that center section. A ball bearing, when it's spinning, everybody spun a skateboard wheel or a rollerblade wheel or a bicycle. If you have ball bearings, they make noise. So just to give you an example, this is a brand new bearing. Now, obviously, if we put oil on this, it's going to quiet down a little bit. But part of the things, or partially some of the questions we get and some of the things that people dislike are the fact that when they shut their truck off, you now hear a lot of bearing noise. So if you have a ball bearing turbo, picture that sound connected through metal. You know, you got that resonating through an exhaust pipe. That's hard to the center section, that's hard to the turbine shaft, that's all connected to the exhaust all the way through the back of the vehicle. So when you turn it off, as I said, these can spin even at idle 5,000 to 10,000 RPMs. So if that turbo is sitting in there just zinging away and you shut the key off, you are going to hear it. You know, if you're standing back by the tailpipe, you're going to hear that thing spooling down. They're not broken. That's totally normal. When you're driving the truck, you're obviously driving the vehicle, you're obviously not going to hear it. So, you know, you're not going to hear that in motion driving down the road. That's just going to be something that you may hear when you shut it off and say the turbo's spooling down, everything's, you know, turning off. They are a little bit noisier in that aspect. It's not a problem. It's perfectly fine. It's not a big deal. But yeah, that's one question we get quite a bit with ball bearings. Another thing that is a huge misconception is a lot of people think that there are rubber seals in turbos. There are a couple in them, but we get a lot of people who will think, oh, well, it's leaking out the exhaust side. I think I got a seal blown out. Well, as I just showed you guys, the seal on the turbine is a ring seal. So it's basically a piston ring seal. So obviously that's not really going to blow out. So if you do have an issue with the turbo leaking out the exhaust side or something like that, it's probably either due to return oil not draining good and say backing up and then pushing past the seal, or it could be a coking issue. It could be an issue where, like we just went over with that ball bearing stuff, it could be an issue where that ring seal is just compressed and it's coked up because you might have drove it and caused the issue, or it might have cracked or something like that. So there aren't rubber seals back there, just so everybody knows that. There is a rubber seal on the front side. So this is the compressor side. This would be where that's essentially how that sits. This is the compressor side of the center section. So in behind this cup, this piece presses in here, and it actually is a part of what holds the bearing cartridge in the center section. There is a O-ring seal that goes around that. But on the inside of, say, where the shaft goes, once again, there is a piston style ring seal inside the middle there. So yes, there is, you know, a rubber seal in here, but you still have another piston ring seal. All right, so now that we've covered the reliability and some of the general questions that we get and concerns that we get, I want to really go over what sets some of the stuff that we do apart from other companies as far as turbo design, manufacturing. That's a big thing for us anyway. Because honestly, a lot of what we do as a business, if we can't improve on something, we normally don't waste our time and energy on it, you know. So really everything that we do, we try to improve on. So as I said, on my right here is a torn down Emperor turbo that is for a drop-in setup that we do for the 6.7 Power Stroke. So this unit is based around, very loosely, based around a BorgWarner S300 style turbo. And the center section, the way we do it is we have this turbo available in journal and ball bearing. So we machine it differently, obviously, for the ball bearing cartridges to go in, but essentially packaging wise, totally same turbo. The one thing that we do that's different than everybody else on the market with this frame and style turbo is the fact that we offer it in ball bearing. I believe we are the only ones that currently do so. So we did a lot of testing on it, went through a lot of different variables, and, you know, landed where we are now. The big thing that we're going to focus a lot on is, and we did focus a lot on, was picking the proper bearing. So I know that sounds really dumb, but there are a lot of options on the market. There's a lot of different bearings used in many different ball bearing turbos. The biggest thing is these are ceramic ball and steel cage, steel center, and there's a lot of other companies use ceramic as well. The biggest difference is where they're manufactured is what we found, because these are made in Germany bearing, and we'll get some up closes to that, but that's all we use. Germans are very high precision. You know, even when it comes to them manufacturing just automobiles in general, German bearings are extremely high precision, very high tolerance, or very, I guess, low tolerance. And it always ended up being a better, more reliable bearing. We've ran everything from Japanese, Chinese bearings to what we fell on here, which was a German-made bearing. The other thing that you'll find in other ball bearing turbochargers that I disagree with is they'll even run steel ball bearings in some of them. And honestly, for me, and from an engineering standpoint, it defeats the whole purpose of it, because you're trying to make it lightweight, trying to make it spool quick. The ceramic ball bearing, if you pick it up by itself, it weighs literally nothing. So it kind of defeats the whole purpose. But yeah, one of the major things, obviously, in the ball bearing turbocharger is selecting an awesome ball bearing. So we pride ourselves on that. We have a great way to assemble the turbochargers and keep everything at a very good tolerance and make it repeatable. That's another big thing. So to my left here, I have our Strike turbos. They are a VGT style turbo. It's a drop-in turbo for the 6.7 Power Stroke. So clearly, these turbochargers are drop-in, and they're essentially the factory style turbo that the trucks came with. There's a lot of differences. They look a lot alike, you know, from the stock form, but a lot of the differences that we have in this turbo are internal. So early on, we did a lot of modifications to the factory turbochargers on these trucks. So we would actually have the customers send turbos to us in stock form. We would modify them, change a bunch of things to help with reliability, to make them just operate better and make a little bit more power, and then we would ship them back to the customer, which works great, but it's a timely process. So that kind of pushed us into the whole, let's make our own. So we ended up taking all the things that we learned and fighting with problems that they had, the things that we would constantly have to change or make better, and put that into the turbocharger that we were producing. So as I talked earlier, one of the key things in the center section was going to a 360-degree thrust bearing. That was a big deal. We went to a billet compressor wheel, so we're changing size of the compressor wheel, the size of the turbine. It's a huge thing. Obviously, we want to do that. The turbine side. So this is one of the big things that we've kind of pride ourselves on for our particular factory replacement VGT. So if anybody is familiar with a VGT, you can kind of look in here and see that there's vanes in here. So these vanes direct your exhaust flow. So the turbine is sitting in here. I'll try to best depict this for you as I can. But the turbine's basically sitting in here like this. And we are directing the exhaust flow that's hitting the turbine to drive it with the vanes. So the way that happens is there is a VGT solenoid on the center section, and there's an armature that sticks in here, and it actually moves this unison ring. And this ring, as it moves, it changes the direction of the vane. And by tightening the vane up like that, it creates more exhaust velocity. So in a VGT turbo, when we need more exhaust velocity to spin the turbine up quicker at low RPMs when you're not moving as much airflow through the motor. You have less actual exhaust volume. So to increase the velocity, tighten that up. It basically changes the AR real quickly at the turbine itself to help drive it quicker. So, and this is included in the factory turbo, but there's issues with this. So if anyone has ever had a 6.0 Power Stroke or some of the earlier VGT turbos, you're going to know about the unison ring sticking issue that was really common. Well, a lot of that issue is because of the material of the unison ring. The tolerance was incorrect. There was a lot of things that would cause that to stick. And what happens is if this unison ring sticks and doesn't move, it really messes with how quickly the truck spools up. It drives like crap. It's a huge problem. So the big thing that we do is tolerances and materials. So our center assembly and our turbine housing is cast and designed in a certain way to have the proper tolerances. The other thing that we do is, you'll notice this is a big deal for us. This is not magnetic. So the cage that we keep our unison ring encased in and the vanes encased in, they're all made out of the same material. So we don't just have, say, a stainless and unison ring and a steel basket to hold everything, or vice versa. We're actually using a similar material for both so that your expanding and contracting is the same for everything, and your tolerance at that point basically stays the same through all operating ranges because everything is moving at the same rate. So that helps us eliminate the sticking issues. It makes everything way more reliable, and it's just overall better. So that is something huge that we really pride ourselves on with these turbos. So there's that. Clearly, if we want to make more power, we need bigger compressor wheels. We do change, obviously, the machining because the compressor wheel is larger in the compressor housing. The housing AR ratio also changes, and that's basically our area radius as far as the internal, let's call it, snail design of the compressor and the turbine. The AR ratio it's kind of a big deal because it creates more flow, less flow at different RPM ranges or different flow rates, etc. So that changes. We basically optimized these turbochargers around what we were trying to achieve, which was adding a little bit of performance, adding reliability, creating a nice package that would drop right in and just be overall reliable and good at making power. So we feel we achieved that pretty well with these. But that's just a basic understanding of, what a little bit of this entails for us from an engineering standpoint and what we look at when we're trying to either modify or manufacture turbochargers. So yeah, so the main thing that I want to kind of sum up for this whole Turbo Tech today is we really wanted to make the customer understand the differences in bearing packages, the reliability, the why you may pick one over the other, what happens when they fail. That I think is a big thing. And basically just give you guys a little bit more knowledge so that if you do have some questions that you may want to ask yourself before purchasing a turbo, whether it be from us or anybody, you kind of have an understanding of what you're looking at and what may work best for you. So I think we need to do another Turbo Tech video not too long after this because I want everybody to watch this, comment, ask some questions, let us know what you think. What did we not cover that you wanted us to cover? Because we could go on with turbos. This video is really difficult for us, but for me, because I could go on for days about turbos. How deep do you want us to get into it? I kind of want to feel that out a little bit. So comment, let us know if you have questions, comment on there, tell us what you think. What do you want to see? Do you want to see other turbos that we sell, the insides of them? We're in and out of these things on a daily basis. So I'm more than happy to share what we got going on and the processes and everything that we do. So let us know what you think, and then we'd be more than happy to make another video and kind of go over those things. In the meantime, if you want to call in and you got questions, feel free to do so. Shoot us an email. You know, if you just want to criticize us, that's fine too. Give us a call. Let us know what you think, and yeah, we'll keep doing more of these, and we'll catch you on the next one.